In this lesson, we'll take a look at right triangle-based trig definitions of trig functions. We'll take a look at the trig functions of angles that are not necessarily in an XYZ rectangular coordinate system, but they're liking to such. For example, previously the sine of some angle theta, and we called it theta, here we're calling it A, that's equal to y over r, which is now the opposite over the hypotenuse. The cosine of angle A is x over r, the adjacent over the hypotenuse, and the tangent of angle A is y over x, the opposite over the adjacent. So notice we still have the x, y, r relationships, but we've added this opposite, adjacent, and hypotenuse. So here's where that comes in. There's something called, and here again, this is a mnemonic device to remember these trig functions, and it's called Chi-Sokotoa. I don't know if you actually heard of this or not, but I use it in my courses. So what it alludes to is the fact that the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So notice we also have our reciprocal functions, right? And the reciprocal of sine is cosecant. So notice how everything is reciprocated. The cosecant is the hypotenuse over the opposite. The secant is the hypotenuse over the adjacent, and the cotangent is the adjacent over the opposite. We use this saying when we set up our trig functions. So we're going to be setting up our trig functions and solving them. So this Chi-Sokotoa will play a part in just a second. So let's take a look at this first example. It says if a right triangle theta is equal to 14 degrees, and a right triangle theta is equal to 14 degrees, and the side adjacent to theta, it has a length of 7, how long is the side opposite of theta? So notice here's a right triangle, and it can be basically be drawn in any orientation. I'm simply choosing to orientate my right triangle as such. So I'm always going to designate the right angle with the box. As we take a look at angle theta, so remember we talked about acute angles, and acute angle is no more than just a reference angle. In this particular right triangle, the sum of the angle measures of the interior angle should be 180. If this is a 90-degree angle by itself, then these two angles would have to be less than 90 degrees. So we can arbitrarily choose any one of these acute angles as our angle theta. So I'm going to choose this as my angle measure theta, and this angle is going to equal to 14 degrees. So now that we have theta is equal to 14 degrees, I can label my sides according to my reference or my given angle measure. So here's some of the steps for setting up a trig function. To set up a trig function, the first thing you must do is choose a reference angle. And remember, a reference angle is any acute angle. So I'm choosing this as my reference angle, theta. In this instance, I'm given the actual angle measure, which is 14. After we choose a reference angle, The next thing we want to do is label the sides of the triangle. So I'm going to label all my sides. So the first thing I actually like to label is my hypotenuse. That's always the easiest. The hypotenuse is across from the right angle, always. The next thing I'm going to do is I'm going to label my opposite side. The opposite is the side length that's opposite your angle measure. So this side length is my opposite. And by process of elimination, lastly, I have my adjacent side. So now if I reread through, it says in a right triangle, theta is equal to 14, which I'm given, I've already labeled, and the side adjacent to theta has a length of 7. So now that I've labeled all of my sides, I know my adjacent has a length of 7. I'm asked to find how long the side is opposite of theta. So I'm actually want to find this length. So we've chosen a reference angle. We've labeled all of our sides. The next thing we're going to do is set up a trig function. And we're going to use Chief Sakatoa. So now let's take a look at what we're given and then take a look at what we're trying to find. So I'm given that my theta is 14 degrees. So I'm given my reference angle. I'm also given that the adjacent side is equal to 7. Now, what am I trying to find? Well, I'm trying to find the side that's opposite. So taking a look at what I'm given and taking a look at what I want, I have to use the adjacent and the opposite. So I'm going to go over here and consult Chief Sakatoa, and I'm going to find out which trig function has an adjacent and an opposite. So in the first part of this, in Chief's side, this is the sine, which is the opposite over the hypotenuse. That's not what I want. Is it a cosine function? Well, the cosine is the adjacent over the hypotenuse, and that's not what I want. Lastly, the tangent is the opposite over the adjacent. So I know my adjacent, I want to find my opposite, so I am using a tangent function. So I'm going to use this last part, the tangent of some angle is the opposite over the adjacent. All right. So now in theory, this is how this is going to look. Well, I know what my given angle measure is. It's 14 degrees. So I'm going to write this out as the tangent of 14 degrees. That's equal to the opposite, which is what we're trying to find, divided by the adjacent, which we were given as 7. So now that I have my trig function, I'm going to solve it to find the length of the side opposite. So the first thing I'm going to do here, and what you should always do if you're dealing with the fraction, you should always multiply both sides by the denominator. So in this case, I'm going to multiply both sides by 7. Notice on the right hand side the 7's cancel, and I'm left with the opposite. So now in the calculator, if we evaluate it, notice that I am using degree measure, so you want to make sure that your calculator is in the right mode. So I am in degree mode. If you were in radian mode, you would get a completely different answer. Just make sure you're in the right mode. And this is 7 times the tangent of 14 degrees, which is 1.745. A 10-foot long piece of wire is attached to the top of a pole at one end and nailed to the ground at the other end. If the wire makes an angle of 30 degrees with the ground, find the height of the pole. All right, so we're going to construct a rough sketch. So first off, we're given a pole, which we don't know the height of. This is actually what we're trying to find. And to the top of that, there is a wire that's attached. And it says that the wire hits the ground and makes a 30-degree angle with the ground. And here we have our right triangle. We're also given that the length of the wire is 10 feet. Right, it's a 10-foot length of wire. And we're asked to find how tall our pole is. Okay. So here we're going to set up a trig function. So in order to set up a trig function, the first thing we must do is choose a reference angle. So we have a right angle, we have an angle that we don't know, and we have a 30-degree angle. We're going to choose the 30-degree angle as our reference angle. The second thing we're going to do is we're going to label the sides of our right triangle. So I always like to start with the hypotenuse. It's always opposite the right angle. The side length which we're trying to find, this is actually the opposite, right? It's opposite our reference angle. And then lastly, we have our side adjacent. So now the next thing we're going to do is set up a trig function. All right, so just remember Chief Sakatoa. All right, so let's take a look at what we're given. Well, we're given the hypotenuse, and we're also given the reference angle. We're given 30-degree angle. What are we trying to find? We're trying to find the side opposite. So I want a trig function that has the opposite and the hypotenuse. So the very first thing in Chief Sakatoa, it says that the sine function is the opposite divided by the hypotenuse. Right? So the sine of any angle, in this case, angle A, that's going to equal to the opposite over the hypotenuse. So we're going to write that out in practice as the sine of 30 degrees. That's equal to the opposite, which we don't know, divided by the hypotenuse, which is 10. In order to solve, we want to multiply both sides by 10, right? We always multiply both sides by that denominator. And if we pull up the calculator, I'm going to put this in as 10 times the sine of 30 degrees. And we get 5. Here we're given a Washington Monument example. It says a Washington Monument is 555 feet high. If the angle of depression from the top of the monument to a certain point on the ground is 60 degrees, how far is that from the center to the base? How far is that point from the center to the base? Assume the base of the monument is on the ground, round to 2 decimals. All right, so first let's talk about angle of elevation and angle of depression. And in both angle of elevation and angle of depression, you need what's called a horizontal line of sight. So here's that concept. If you have a person, and let's say for that person or for everybody, this is your horizontal line of sight. Okay, it's that line of vision where you're looking exactly straight forward. If you were to turn your head and if you were to look up, that is called an angle of elevation. For an angle of depression, that same individual would have a horizontal line of sight. And from that horizontal line of sight, if you look down, this is the angle of depression. All right, so no matter if it's an angle of elevation or an angle of depression, each must have the exact same horizontal line of sight. So we take a look at our example. The Washington Monument is 555 feet high. So I'm just going to sketch out that Washington Monument. And this is 555 feet high. If the angle of depression from the top of the monument, so at the very top of the monument, right, if there were a person standing there, their horizontal line of sight would extend this way, correct? So an angle of elevation, they would actually look down at the ground. So this would be our 60-degree angle. All right, this angle. All right, so now that I have that constructed, we're also asked to find how far is that point, which would be this point here, from the center of the base. So we want to find this distance. All right. So we're going to set up a trig function. So the first thing we have to do is choose a reference angle. Well, now if I look very closely, I'm going to actually blow this up. My triangle, all of my dimensions are inside of this triangle, not outside. So for example, if this is a altogether 90-degree angle. I'm going to draw my box in here. From the Washington Monument, if that's a 90-degree angle, if this angle is 60, then this angle has to be 30. So I'm going to use this 30-degree angle as my reference angle. Okay, so I'm going to clear this up just a little bit. All right, so now it looks something like this. So notice now, originally I was given 60 degrees for the angle of depression. Altogether, that angle of depression, which is 60 degrees plus this 30 degree, that gives me that 90-degree angle. So this is my reference angle, which is 30 degrees, not 60. The second thing I'm going to do is I'm going to label my sides. So firstly, I'm going to label the hypotenuse. Next, I'm going to label the opposite. All right, so notice since my reference angle is now here, the side opposite my angle is my opposite side, and the Washington Monument's length is my adjacent. So now we're going to set up a trig function. Okay, so we're going to control C Sakatoa. So now what are we given? Where we're given the reference angle and we're given the adjacent. What are we trying to find? We're trying to find the opposite. So I'm looking for a trig function that has both the adjacent and the opposite. So I want to use a tangent function. So I'm going to write this out as the tangent of 30 degrees. That equals to the opposite over the adjacent. And now I'm just going to solve it for the opposite side. So I'm going to multiply both sides by 555.